Hello, everyone. So again, welcome to the END Applied Research Talk series. Today, we're super excited to have Professor Song Han here with us to talk about recent advances in efficient transformers. Today's event is a Teams live event. So during this talk, if you have any questions, please type those into the Q&A panel that you can see in your Teams application. And then we will follow up there and then moderate those questions for you. The talk will be recorded and released after this talk. Yeah, and then so that's pretty much it. And then right now, Longqi will be started to introduce Professor Song Han.
Great. Thanks, CJ. So it's my great pleasure to introduce Professor Song Han from MIT Department of Electrical Engineering and Computer Science. So Professor Han's research focuses on efficient deep learning computing, and I believe many of you already know his work on deep compression and efficient inference engine that have significant impact in academia and industry. And he's also the recipient of many prestigious awards, such as NSF Korea Award, MIT Technology Review 35 under 35, and Best Paper Awards from multiple top conferences. So it's really great to have you here, and we're very excited to learn from your recent work. So Song, please take it over.
All right, thanks. Thanks, Longqi, for the introduction, and I'm very glad to present our recent work on efficient NLP at Microsoft. Okay, so this is our recent research topics on focusing on TinyML and also on efficient deep learning. So we focus on model compression, neural architecture search. Our AI design AI has outperformed the human performance in multiple low-power computer vision challenges, bringing both low latency and also high accuracy, such as proxy-based NAS and our second generation of neural architecture search, the once-for-all network. We also focus on efficient AI applications, such as efficient NLP, efficient vision. For example, today I'm going to introduce our recent work from Hanrui on efficient machine translation, and also work from Zhijian on the Lite transformer, also for machine translation. We also have an area of research focusing on the efficient hardware for AI and also AI for EDA. So our research topic is full stack research, from training to inference, from edge to the cloud, from algorithm to the hardware. And this is a full spectrum of our view. We believe for efficient AI, we should really focus on the full stack design, which bring a larger design space and more opportunities for researchers to design across different areas. So this talk, we will focus on the edge for efficient inference on the algorithm side. And we'll introduce two papers, the HAT, hardware-aware transformer, and also Lite transformer. Okay. So transformers are ubiquitous, both on the cloud and on the edge, such as the chatbots, machine translation, etc. However, they are very computationally expensive, especially in recent years. From 2017, the transformer, roughly 50 million parameter model size. And in 2018, this number surges to over 1 billion by GPT-2, right? And NVIDIA further expanded to 8 billion in 2020. And very recently, OpenAI further increased the model to 170 billion parameters, right? So this is a huge increase of both the model size and also the computation, right? Which makes it very inefficient to process on small embedded devices like Raspberry Pi, right? It takes 20 seconds to translate a 30-token sentence with the transformer big model, right? So 20 seconds, the user experience is pretty poor. So how can we solve this issue? How can we have more efficient transformers? And even worse, right? To improve the accuracy of transformer just by a little bit, previous work from neural architecture search to search efficient transformers is very inefficient. As a paper published in ACL last year reporting that training a single AI model can emit as much carbon as 5 cars in their entire lifetimes, right? So this is really a lot of CO2 emission due to the, you have to train so many models and to search for the best one out of it, okay? So it mentions that deep learning has an outsized environmental impact, right? So in this year, we provide a solution, right? ACL, we want to have green AI, right, to reduce the design cost for neural architecture search, and also tiny AI. So during inference, we want to have tiny, small models that can fit in embedded devices, right? So we reduce the search cost from 250 GPU years, and we save it by 4 orders of magnitude, with only 52 pounds of CO2 emission of GPU compute cost, right? And we can achieve even better solution. And so this is the main idea of this talk. So we have provided 2 solutions, okay, to bring efficient NLP. The first one is HAT, the hardware-aware transformer, an efficient NAS method for transformers. The second one is a Lite transformer, which is an efficient primitive, efficient primitive to provide a low computation but high accuracy. Okay. So we'll start with the first one, the HAT, hardware-aware transformers for efficient NLP. So in this work, we focus on efficiently search efficient transformer architectures. Okay, so there are 2 efficient here. So efficiently search means we search rather than taking 250 GPU years like the previous work Evolved Transformer does, which will cost $5 million of cloud compute GPU cloud compute cost and 600,000 pounds of CO2 emission. Right, so we get rid of the meta controller and used the weight sharing method and present a SuperNet, the SuperTransformer based method, so that we can decouple training and search, which I will discuss in detail, which take only 184 GPU hours and only hundreds of GPU cloud compute cost, which is very affordable in academia. Okay? So that's efficient search. And finally, we want to search an efficient transformer architecture. Right? So rather than taking a long time to execute, we make it faster and also smaller model size and also smaller flops. Okay. So by using a hardware latency feedback in the search loop and also proposing a novel design space. So what makes the hardware aware very important? Okay. So there are several pitfalls. The first pitfall is the flops cannot reflect the real latency. For example, in this figure, we plotted the flops in the x-axis and the latency in the y-axis. And here we tried different methods to shrink the flops from about 320 million flops to 180 million flops. We tried to scale the number of layers in blue and also the number of hidden dimensions. Okay. So when we are scaling the number of hidden dimensions, we can find the latency doesn't change pretty much on the CPU. Well, layer scaling, number scaling, shrinks the flops, but also shrinks the latency. A second pitfall is different hardware has a very different strategies or different factors impact different hardware. For example, the Raspberry Pi, the latency is greatly influenced by the hidden dimension, as shown on the left-hand side. The latency drops quickly. While the GPU is not influenced by the hidden dimension size due to the high parallelism, right? And GPU is very good at processing super large matrix multiplication. So even if you shrink the dimension by and shrink the flops, the total latency will not change much. So that motivates us to propose the hardware-aware transformer to take into account different hardware's parallelism and hardware characteristics. Okay? And another motivation is AI needs to be deployed on diverse hardware platforms, both the cloud AI, the mobile AI, and also the tiny AI. Right? And these different scenarios have quite diverse computational resources. Like the cloud AI, you have tons of memory and teraflops or even petaflops of computation. Well, on the mobile device, you have about several gigabytes of memory and several or tens of hundreds of gigaflops per second. Well, on a tiny ML or microcontroller, you have like only 100 kilobyte of memory and several million flops per second. So the computational resource is quite different, and it is not efficient or even not possible to just train one transformer model that can fit every device. So this is the conventional method, the general transformer for all hardware, right? It has low efficiency. And we are proposing here to have a specialized transformer for each hardware device, right? Specialized means more efficient. But we also want to save the overhead of designing different models for different hardware, right? Can we have just one SuperTransformer that can born many children, many SubTransformers that can be specialized into different hardware and save the design cost? And that's our goal. And let's revisit how, the conventional methods to search, to do neural architecture search and compare the design cost with just train one model. So this is the cost of GPU hours to just train a mobile net. You just do forward and backward and train a mobile net for a 2019 Galaxy phone, right? But if you do neural architecture search using conventional method, right, which require a microcontroller, it adds another for loop outside the expensive training forward and backward for loop, right? So it's very expensive. You search 1,000 models, you have to train 1,000 models, which is pretty expensive. Even if you train on a smaller data set, it might sacrifice the performance and also take a long training time. And if you have multiple devices, right, you want to target a 2019 phone, 2013 phone, consider different customers may use different phones. That's another for loop outside, which makes it even more expensive. And if you have more devices ranging from the cloud and tiny, you have another many devices, another expensive for loop, right? So this resulted in a large training cost measured both in GPU hours and also the tons of CO2 emission. Okay, so how can we solve this issue? How can we just get rid of those expensive for loops outside those training loops? And the solution here is decouple the training and search. Okay, so rather than on the left-hand side, you have a microcontroller outside the training for loop, we decouple training and search. Okay, so we just train a SuperTransformer only once. Okay, and that overhead is just done only once. Okay, and then when you are having different devices, you have different search episodes, we just sample from the pre-trained SuperTransformer. Okay, we get several SubTransformers. Okay, we put in the hardware latency feedback, etc., and then we do evolutionary search. And we use a predictor to predict the accuracy, so no training is required here. Okay, which saves a lot of training cost and makes the total cost very low. And as a result, we decouple training and search. So for all these different scenarios, we can just train one SuperTransformer, okay, and greatly reduce the search cost from 880 million GPU hours to only 400 GPU hours. Okay. And these are the 3 steps in HAT: train a SuperTransformer, and then decoupled with the search process, which basically contains evolutionary search and also the SubTransformer, training the SubTransformer from scratch. And for GPUs, we can deploy a larger SubTransformer. For a mobile phone, we can pick a mid-sized transformer. And for a tiny microcontroller, we can pick a tiny SubTransformer. And all these are subtracted or selected from the SuperTransformer. So the challenge here is how do we design and train the SuperTransformer? First of all, we design a better design space, breaking 2 conventional design rules. The first rule is the information bottleneck. Conventional method, you have an information bottleneck between the encoder and decoder. Now we allow arbitrary encoder and decoder attention. Let's watch the video again. So here we can allow arbitrary encoder and decoder attention during the training. And the second convention is all the layers are identical in the previous designs. And now we allow heterogeneous layers where both the encoder and decoder, different layers, you can have different sizes. Okay, and different size can fit very well with different hardware architecture due to the different cache line, different SRAM, different number of PEs, etc. And another key question is how to ensure that we can pick different sizes and still it works pretty well. So here we allow, we support elastic embedding dimension. Okay, so SubTransformers with different sizes share the front part of the embedding vector. We also allow elastic number of heads in the self-attention and also cross-attention. Okay, we can have 2 heads, 4 heads, 1 head, 8 head, right? With random sample different scenarios during training. We also support elastic hidden dimension. You can have like a quarter dimension and a half a dimension or 3/4 of the whole dimension during training. And we can also have elastic number of layers. We can have 2 layers, we can have 4 layers. For GPU, we can have like more layers and larger dimension. For Raspberry Pi, we can have a smaller dimension, right? So it's fully elastic. So we have elastic number of layers, elastic hidden dimension, elastic number of heads, and elastic embedding dimension. So during training, each iteration we just randomly sample one of such configurations. Okay, it can be a large model, it can be a small model. They share the weights as a very strong regularization, so that during inference we can pick any of them. For Raspberry Pi, we can pick a smaller one. For GPU, we can pick a larger one, right? And on the accuracy side, this is a strong regularization similar to dropout. We are just dropping off the embedding dimensions, the hidden dimensions, the number of layers, and the number of heads, right? You can imagine here, during the random sample, we can drop some of the layers, and increase some of the layers, and drop some of the layers. Also for the hidden dimension, the number of heads, and also number of embedding dimensions. Okay. And at inference time, we just sample a subnetwork from the SuperTransformer. Okay. Since the SuperTransformer is trained with elastic dimensions, we can pick a smaller one for IoT device and pick a larger one for the GPU. And since they share the weights, they have a very strong regularization to maintain the accuracy, even for the smaller subnetwork. And we find such a SuperTransformer. If you pick a SubTransformer from such a SuperTransformer, the validation loss is a pretty good proxy as the SubTransformers trained from scratch. You see the blue score. If the loss is pretty small, the blue score is also higher. Okay, so that's the first step of training the SuperTransformer. Okay, we just train a large SuperTransformer that can have elastic dimensions, elastic hidden dimensions, elastic number of layers, elastic number of heads, right? So we are now fully prepared. We are equipped with a SuperTransformer that we can just pick, sample those SubTransformers, and they still work really well. And different SubTransformers, their loss on the data set is a good proxy as the transformer trained from scratch. Okay? So that now we can perform evolutionary search. We just randomly pick different SubTransformers and apply evolution with crossover and mutation to see which is the best fit. Best fit means both high accuracy and also low hardware latency. Okay. So during evolutionary search, first the evolutionary search engine proposes a SubTransformer architecture, and we get the weight of the architecture. We get the weight of the architecture from the SuperTransformer. We directly pick the pre-trained weights according to the proposed SubTransformer architecture from the SuperTransformer. And we get a validation loss. Okay. And on the other side, the SubTransformer architecture is fed to a latency predictor that can predict the latency, how fast does it run on the target hardware. So now we get both the validation loss and also the hardware latency as a feedback to the evolutionary search engine. Okay. And here we want to emphasize the latency predictor. Why do we need a latency predictor rather than just measure the latency directly on the hardware? Okay, so directly measuring the latency is very cumbersome. You have a heating issue, right? The mobile phone will get really hot after a while, and will get slower when it overheats, right? And also we have a limited number of devices. The parallelism is not enough, and we cannot afford to buy a whole farm of devices to measure their latency, right? And they also can be slow. Since during evolution, we want to have a feedback very quickly. We don't want to have the latency feedback to be the bottleneck of the search process. Therefore, we train a latency predictor that can provide a very fast latency feedback. Okay, so this latency predictor is just multiple FC layers, fully connected layers, and the input feature includes the number of layers, the embedding dimension, the number of heads, etc. Basically, the architecture or the dimension of the SubTransformer. Okay, and the final regression result is the latency. Okay, so it is trained with a subset of the SubTransformer architecture and measure the latency. Okay? You still have to measure a lot of latencies to collect the data set. But after the data set is collected, you can use it many times during the search process, during the evolutionary search process. Okay? And this model can be quite accurate. The root mean square error is just 0.1 seconds, 100 milliseconds. Okay, you can see the x-axis is the real latency, the y-axis is the predicted latency, and the line is y equal to x. It's pretty, the dots lies really well on the y equal to x line. Okay, so now we can search a pretty good architecture. To achieve the best accuracy, we want to train the SubTransformer from scratch to get the final accuracy. Okay. So this is our result, comparison with the baseline transformer measured on the English to Germany running on a Raspberry Pi. Okay. So x-axis is the latency, the lower the better. The y-axis is the blue score. The higher the better. Okay? So the blue line is just shrinking the transformer big by dimension scaling. We just scale the dimension to get a smaller transformers and even smaller transformers. Okay? And the orange line is by scaling the number of layers on the baseline transformer. Okay? And the red line is our result, the hardware-aware transformer. Okay? We can see the hardware-aware transformer HAT can achieve 3x speed up and 3.7x smaller size over the baseline transformer. And here's the result measured on the NVIDIA GPU. So again, this is very similar setup. HAT can achieve 2.7x speed up compared with the transformer base. And to make the result more convincing, we experimented with more data sets and more hardware devices. The data set here include the English to Germany and also English to French. English Germany on the top, English to French on the bottom. And here we have the Raspberry Pi Intel CPU and also two NVIDIA GPUs. Okay. And you can see HAT consistently outperform the baseline transformer, transformer big and transformer base by between 2 to 3x speed up. And here we visualize the difference of the architecture that is specialized for Raspberry Pi and also for NVIDIA GPUs. We can see here for the Raspberry Pi, we have 3 decoder layers. Well, the searched model on the GPU has 4 decoder layers, and the hidden dimension is larger on the GPU than on the Raspberry Pi. The model size is also larger on the GPU than on the Raspberry Pi. The interesting thing is both models achieve the same blue score. but they have quite different architectures. The reason is GPU has much more parallelism than the Raspberry Pi. So it picked more a number of layers and also more hidden dimension with a larger model size. Okay. And the amazing thing is even the smaller model for Raspberry Pi can also achieve the similar accuracy, the same accuracy. Both are 28.1 BLEU score compared with the GPU model. And here we want to emphasize that a specialized model is really important. So the diagonal latency is the lowest. So now we have two hardware platforms, the GPU and the ARM CPU. And also we have two models, the model specialized for GPU and the model specialized for ARM CPU. Well, both models are, the architecture is picked from the same SuperTransformer, but they are two different SubTransformers. And we can see the transformers specialized for the GPU works the best on the GPU and is slower on the CPU compared with the model specialized for the CPU. The model specialized for the GPU is 147 milliseconds. With the same BLEU score, the model specialized for the CPU runs 184 milliseconds on the GPU. Okay, so specialization is very important. So this is the comparison with the evolved transformer, the baseline that we compared. So by saving the search cost by for orders of magnitude, we can also achieve the efficient transformer. With the latency have a 2.7x speed up. The model size is 3.7x smaller. The flops is 3.2x smaller, and the search cost is 4 orders of magnitude lower. And the key reason for such low search cost is due to decoupling training and search by weight sharing. Okay, we just train one SuperTransformer and we pick SubTransformers from there. And since we target green AI, so we also translated the search cost to the GPU, to the CO2 emission just by multiplying the factor. The factor is provided in ACL 19 paper. We reduced the search cost from 600,000 pounds of CO2 emission to only 52 pounds of CO2 emission, less than a human life for 1 year. Okay. We also compared with other models on the WMT14 dataset, including the transformer, evolved transformer, Levinstein transformer, and also ours. So we have a lower latency, which is on the left axis, and also a higher BLEU score, which is on the right axis. So the bar is the latency, the lower the better, and the curve is the BLEU score, the higher the better. So HAT is focusing the architecture of transformers. What about combining the efficient architecture search with the model compression techniques, including pruning and quantization? Okay. So we can find these two techniques are orthogonal, and if we combine together, we can get even better result. Right? So transformer base, the transformer has 700 megabytes. Right? Pretty big, almost a gigabyte. Can now fit a mobile phone really well. You have to download a long time if you download the model from Apple Store, right? And HAT, using our efficient architecture search, we can achieve a better BLEU score, but reduce the model by 3 times. Now it's 200 megabytes. But 200 megabytes probably still too slow to download from Apple Store. It will take you a lot of LTE bandwidth, right? And HAT, when we prune it and quantize it to 8 bits, just quantize it to 8 bits, not pruning, just quantize to 8 bits, we can achieve a slightly higher BLEU score, but 57 megabytes. And we can further quantize it to only 28, but to only quantize to only 4 bits. The model size is only 28 megabytes, which is very easy to download from Apple Store now, right? And the BLEU score is 41.1, well maintained from the base transformer. Okay. So HAT is orthogonal to those general model compression techniques and can be well combined together to provide a perfect solution for mobile natural language processing. Okay. And we have open sourced everything. containing both the code and also the many pre-trained models. We released the latency, the blue score, model size, flops are all provided, and provide a push-the-button solution to run the models thanks to Henry's amazing work. Okay, and you're very welcome to check out the code base. In particular, if you're working on product related to NLP on the edge devices, like on the mobile phone. Okay. All right, so let's switch gear from neural architecture search to designing a better primitive. Okay, so we just talked about HAT, which efficiently search efficient model by decoupling training and search by proposing a SuperTransformer. Get rid of the meta controller and introduce arbitrary attention and also heterogeneous layers. Now we introduce a new primitive called Lite transformer with long short-term range attention. It's a paper in iClear 20 work from Zhijian Zhang Hao. Okay. So let's see the transformer framework. Now we present two blocks of the transformer framework here. We have the attention module here in green, and also the FFN layers in yellow. Okay, now we have two blocks. This is the basic view, original perspective. Okay, a base transformer block is formed by attention and two layers of FFN. But we can also have a different perspective of the transformer. Okay, let's see, from here to here, we can just change the dashed line by using a different perspective. So the transformer can be seen as a FFN with a bottleneck attention and another FFN. Okay, and this is the bottleneck is due to in many 2D attention applications in computer vision, the bottleneck can reduce the computation since the number of pixels are pretty large and the complexity of attention is O(n) squared. Okay, but it is unclear whether such bottleneck is effective for 1D attention as well, like in NLP cases. Okay, whether do we really need those bottleneck architecture in 1D attention? So here we profiled the number of multiplication as basically the computation for the attentions and also for the FFNs. Okay, so on the left-hand side there's a base transformer block, and the green part is the attention, which occupied only 44% of the total computation. Okay, and FFN occupied more than half. Okay, but this is not very desirable since the FFN itself does not perform any context modeling, but just take too much computation. And we instead design a flattened version of the transformer block. So we want to put more proportion of the computation to the attention rather than putting it to the FFN, and increase the proportion of attention, decrease the proportion of the FFN layer. So quick comparison, before, after, before, after. Okay. We can see the proportion of the attention layers increased from 44% here to 75%. Okay, 44% to 75%. And the FFN layer proportion decreased from 56% to 25%. Okay. And in this method, to achieve the comparable blue score in the new design space, may also have to new design may also have to slightly increase the computation of the model, but that moves the majority of the computation to attention and leaves a larger space for further optimization for the attention. And now the remaining work boils down to how to shrink the attentions. So we first increase the proportion of attention, and according to Amdahl's law, and then we can accelerate and further compress the majority of the computation, which is attention. Okay. So what does attention learn, and how can we using this domain knowledge to compress it rather than using general purpose pruning and quantization techniques? Now we want to have domain insight. Okay, apply our domain insight to compress and produce a light version of the transformer. Okay. To figure out, we first visualize the attention weights, okay, of the transformer. Okay. According to the previous work, the focus of our attention typically have some strong patterns, like sparse, very sparse, and also have these clear diagonal groups. So words usually are attending very heavily to its adjacent words. Okay. So attention captures both the sparse and global context, and also the diagonal local information. Okay. So these are two patterns. One is the global pattern, one is the very strong local pattern, which is diagonal pattern. Okay. So attention marks extract both global and local information with the same architecture, but requires a large capacity, which is inefficient. So rather than using the same architecture to extract both global and local information, we want to have a specialized version. So this is motivated by the hardware design, where the general purpose hardware like CPUs have more overhead than the specialized hardware like FPGA accelerators. So a specialized design is usually more efficient than the flexible and general purpose design. Okay, so specialization is the key in efficient hardware design. And how can we apply the same method, same principle to transformer design? Okay. So rather than using the just one attention layer to extract both local and global information, we now like attention to only extract the global information for global attention, and use the conv layers as a specialized kernel for local to extract information for local attention. Okay. Now they're fully decoupled. You do something, you just do something that you do really well, okay, and just offload the other stuff to specialized people. Like the local information can be well modeled by the conv layer, right? Since the 1D convolution, by the sliding window, you are capturing those local information. Okay, so in this manner, these two branches are encouraged to have different perspective of the sentence, global and local. So the architecture can benefit from the specialization under a tight resource constraint. When you have lots of resources, that is okay. You have lots of power, you can use a CPU, right? But if you're very energy constrained, you have to use accelerators. So you have to use specialized hardware. And when your flops constraint is very heavy, you have to use specialized attention, like the long short-term range attention, okay? So this is the result for the Lite transformer. So the x-axis is multiplication add, and the y-axis is the blue score on the left-hand side, which is for machine translation, and is the perplexity on the right-hand side, which is language modeling. Okay. So here we compared with the transformer in black and Lite transformer in red, and you see the dashed line in the middle that separate the space into two parts. On the left-hand side is roughly below 500 million max. That's 1 billion, basically 1 giga flops. Okay, for mobile case, and we can see that the Lite transformer can reduce the flops by roughly 2.5x for machine translation, and reduce the flops by 2x for language modeling, achieving similar performance. How about Lite transformer versus AutoML? Again, here we compared with the evolved transformer. The number of parameters roughly the same, 3 million versus 2.9 million. The number of max roughly the same, 94 million versus 90 million. Blue score increased from 22 to 22.5, with better performance. And design cost from 2 million GPU hours to only 110 GPU hours. And pounds of CO2 emission also decreased by 4 orders of magnitude. Okay. And we can further compress the Lite transformers by pruning and quantization. Okay. So we started with the baseline, okay, which is 176 megabytes, and we can prune it to make it only 69.2 megabytes, and further quantize it to 8 bits, and it's only 17 megabytes. You know, so quantize it further, then you can get a model with less than 10 megabytes. Okay, and the blue score on the translation task is pretty well maintained. All right, so this is a summary slide. We presented HAT and Lite transformer pushing the frontier for green AI and tiny AI. Green AI means we want to reduce the design cost, the training cost, the search cost. Okay, you want to very efficiently search a model, and also you want to search an efficient model that is very tiny, taking less computation, less latency, and can work on small devices. Okay. And in particular, we introduced HAT, a better NAS algorithm for transformers, which is hardware aware and can target small embedded edge computation constrained devices by providing the latency feedback. Remember, we introduced the latency predictor, which can replace a measuring the latency with only 1 millisecond, only less than 100 millisecond error. Okay. And also, we proposed the Lite transformer that provides a better primitive, the long short range attention, that use attention to capture long distance and use convolution to capture the short distance information. And by using such specialization, we can make the Lite transformer pretty efficient. And both projects are open source online. You are very welcome to check it out on the webpage and also on GitHub. We also released the presentation on YouTube. You are very welcome to subscribe to our YouTube channel for more presentations and demos. Okay. And with that, I would like to conclude my talk, and hopefully we can push the frontier for tiny ML and efficient AI together. Thank you.